Thanks, Ben. Actually, I decided to change a bit the tag and go back to something which is a bit more aligned with what was presented before to keep in line with the topics that were presented here. So my initial goal was to present some of the, a bit of an overview of the work we do within the lab on really flexible machine learning tools. But then I thought that people here were interested more a bit into going a bit deeper into the methodology, so I decided to pick a subset of what I was initially thinking of presenting and present that a bit more in depth. So this leads me to actually acknowledging two of my PhD students, so one current PhD student and a former PhD student, now professor in China. So we'll see most of the work is the work of these two students, which I'm really grateful to have the opportunity to work with. Another acknowledgement I'd like to make is actually to IPAM for inviting me here, but also more broadly because thinking back, IPAM had a really a substantial impact on my personal career. It started in 2008, where IPAM created a summer school on mathematics in brain imaging, which I did not take part. However, my PhD supervisor at the time got invited and was speaking there, giving a talk on Riemannian manifolds and how this could be used for brain imaging. Which was, and he decided to present some of the work I was working on at the time. And after that summer school, the faculty of the summer school decided to come together and create a special issue in Neuroimage on the same topic, so mathematics in brain imaging. And my PhD supervisor at the time forced me to take one of my work and actually publish this as a journal paper in this, which I was very reluctant to do because I didn't see what the interest was in getting my conference paper and extending that to a journal paper. And it turned out that this paper is actually one of my best cited paper. So it was published again in this special issue and was cited about 1,000 times now. So really grateful to IPAM. I hope the same can happen to the students that I'm presenting the work of today. We'll see. Anyway, more broadly, so what are we trying to achieve in the group? Is again to go back to this idea of having flexible machine learning tools to support decision making, and we do that with a key focus on medical imaging for applications on both preoperative planning, but also on intraoperative navigation and postoperative assessment. In this particular talk, I'll only focus on the more preoperative planning aspect. The challenges that we face are, especially in surgery, is that there's very little kind of standardization of imaging. There are a lot of intraoperative changes to tackle as well. There are some difficulties in really interpreting what's going on, both on the images but also on the output of the algorithms. So these are the sort of topics we address. In addition to this, we need to take into account where the tools that we develop fit in the workflow and really help in decision support without adding too much of a cognitive workload. So this leads us really to this need of developing flexible tools that fit within that workflow, but leave the clinical team in control. So we don't want to replace, we want to augment the work of the clinician really within surgery. So that's really kind of initially what I wanted to present and go through many of these points, but I'll decided to focus this time really on the preoperative planning side. But nonetheless, we need flexible tools there as well. Why is that? So we can look at one example here, whereby we might be interested in segmenting the tumor, as we saw in the previous talk from Ender. One of the things one of the characteristics of this application, if you take it more from a diagnostic perspective, is that you have a lot of imaging modalities available, and you want to make the best use of all the imaging you have to make your prediction. Great. So typically nowadays, you would take your stack of images, feed that to a given machine learning model, and then learn some output segmentation. Great. So in essence, in many cases, what we want is not only the tumor, but we might be interested as well in the relation of the tumor with surrounding tissues, with other kind of anatomical structures. And so ideally, this is what we'd like. We'd like to have a better understanding of what's going on in these images, not only for a specific task, but really for a variety of different potential applications. One of the additional challenges that one of the challenges we face in clinical practice is that for one patient to the next, we might not have all the sequences available for some given reason. Maybe some of the scans was corrupted or had too many artifacts and we couldn't use it for this particular patient, or they could not have any contrast agent for safety reasons. Many reasons make it such that in clinical practice we might not always have a consistent set of modalities to work with. And if we want to roll out these sort of tools really in practice, we need to be able to handle the fact that we have potentially a different subset of modalities to work with, or protocols to work with. So we need to handle this heteromodality within our algorithm if we want to roll them out. There are some obvious ways of dealing with this that I would potentially call naive. So we could just replace that missing modality with zeros or whatever random value. We could also maybe try to impute these missing modalities as a pre-processing step, but then it's become difficult to understand what is the impact of that sort of pre-processing or this sort of missing inputs on the downstream learning tools afterwards. Another challenge, a big challenge that we face, especially if we want to infer different tasks on the same data, is that because we're in medical imaging, training data is always complicated to get, and we can focus on specific tasks such as brain segmentation, and we might have a decent training data set for that. Same thing for, say, white matter hyperintensities, but these are really task specific, right? So they cover only a given task, and they don't necessarily give any additional information in addition to just the segmentation of the lesions in this case. If we're interested in linking that to anatomy as well, or tissue types and so on, there's a wealth of different brain atlases that have been constructed over the years. So there's quite some variability in terms of defining exactly what's brain anatomy, how brain anatomy should be described. There's a lot of variability in terms of how many data sets were used to create these atlases. And in most cases, these really relate to healthy brains. So we don't have any direct link between, let's say, anatomy and pathology. So we have these sort of heterogeneous data sets that exist, that have been acquired with lots and lots of effort and resources that I've put in there. So if we think about merging all that together and starting from scratch, let's say this is not something that's going to be feasible in practice. So if we're interested now in building a data set of brain tumor annotations together with anatomical structures annotations, this is going to be a very, very costly effort. So can we make use, nonetheless, of these heterogeneous data sets is one of the topics we'll cover here. So another challenge as well is that we have actually really a strong need for quality control and some robustness challenges when dealing with medical imaging. So you might be familiar with this quote from Jeff Hinton in 2016, who said that at the time that we should stop training radiologists because basically radiology is a solved problem, right? I don't think it's going to happen. We're almost close. I mean, we're close to the 5-year kind of horizon that was listed there. And I think this comes from the fact that actually if we think of radiology a bit as from a slightly naive approach, yeah, we have images, we have a given task, and we just need to process them, take image in, give decision out, and that's it. But actually things are much more complicated than this, and I don't think we're going anywhere near a solution where everything will be fully automated. So one of the things we wanted to do on our side is keep the clinicians in the loop as much as possible within the tools. So for example, if you take this question of segmentation, so we might have, again, this interesting set of modalities to work with. We can do some automated segmentation from there, but what do we do if anything goes wrong, right? The radiologist or the surgeon, if they were looking in surgical planning here, is looking at these images. Most of it is okay, but some of these might be off. What do we do? How do you correct this? And you don't want to redo all the manual annotations there. So can we think of ways of actually implementing user refinement at inference time so that we can deal with this, knowing that obviously we don't have the ground truth in these categories. Okay, so that's kind of the 3 topics I'll cover in this lecture. So how do we deal with heteromodal inputs? How do we deal with heterogeneous data sets? And how do we deal with user corrections? So let's start with the heteromodal inputs. So again, what we want to do is have, let's say, a convolutional neural network that can take a series of image sequences from the same patient, processes, and give a segmentation as output. But we ideally would like a model that is able to cope with, let's say, missing modalities here. Okay, and we want something that we understand and that can help us, understand also what's going on and have a bit more guarantees as well. So an obvious naive solution is again just to replace the missing images with zeros, but we really there's no reason why this would be kind of optimal. Other approaches have been trying to synthesize missing modalities as pre-processing and then feeding that to the network. But again, we don't know what we don't use that during training, so it's difficult to know exactly what the impact of this synthesis would be on the output segmentation. What we took as a starting point is that, well, a bit similar to what Ender was presenting before, we decided that maybe creating a common feature space to explain all these images together would be a good idea. And if we have this latent space to explain how different images would be created from this latent space, or potentially we could do the same thing and generate as well any missing modality if we're informed by the existing ones. So we'll look a bit into that, and this will lead us to a sort of variational, let's say, encoder-decoder, to not exactly say autoencoder, that can handle this heteromodal inputs. Why is it not an autoencoder? Why do we call that a variational encoder-decoder? Is that we actually use as well the segmentation as a missing modality, and therefore we will never kind of directly encode the segmentation to generate the latent space. So we have slightly different paths in the encoder and decoder streams. So this was really inspired by a really interesting work that was presented in MICAI 2016 to handle this sort of missing modalities. So what the authors did there was essentially to extract features for each of the modalities in an independent manner. So you have independent streams to extract features from there. And then you basically use a simple arithmetic operation to merge the features from these independent sets. And if you use a mean here, then you can see that whether you have 3 or 4 modalities, the mean should be the same, right? So that's what you're trying to get here. And then you can process this averaged feature set with a standard convolutional network and get your output. So that's all great. And in practice, this allows us to deal with missing modalities. However, we don't really have any theoretical understanding as to why the mean is a good one. Right? It seems a good way of merging information, which can deal similarly with different number of modalities, but it's not sure that there's any optimality in doing so. So can we actually try to use some probabilistic understanding and formalize either why the mean is the best way of doing that, or finding alternatives to get a better averaging there. So that's where we inserted our graphical model. So what we decided to do is to take a latent space, have latent features Z here, and from this latent space, we would be able to generate all the imaging modalities, but as well the segmentation. Right? So we treat the segmentation in the same way as any imaging modality for the sake of the probabilistic model here. And now if you try to encode the joint distribution of the latent space and the imaging modalities and the segmentation, you can actually see that there's a way of factorizing it so that you get prior for your latent space and some modality-specific distributions as well, which will be interesting because then we can use them independently here for each of the modalities. So if we feed that into a standard kind of autoencoder approach, then what we would like to do is to maximize the marginal log likelihood of all the imagings and the segmentation together. Right? And so we end up with this kind of intractable logarithm to deal with. So Ender showed us just in the previous talk that a typical way of dealing with this in practice is to use the elbow. So that's what we do here as well. So we introduce an additional parametric distribution, Q of phi here, which is just modeled as a Gaussian, and which where the mean and the standard deviations are essentially given by a network, right? So we encode the images, or the images are fed. We get a mean and standard deviation, and this gives us the distribution of Q. And then within the elbow, this is what we get. So we end up with a term which is a reconstruction loss, and a regularization term where we measure the discrepancy between this Q distribution and the prior distribution for the latent space that we arbitrarily fix here to a Gaussian for simplicity. Okay, so that's the standard VAE. We don't yet have a way of dealing with multiple modalities and potentially missing modalities. So what do we do here? So, whoops. Yeah, so we go back to our probabilistic model here, and we now look at the distribution, the distribution of our feature space that we factorize into modality-specific distributions, and we do the same thing for the Q distribution that we use for the within the elbow. Right, so we have this kind of modality-specific probability encoder, and then what we actually have is that if all of the individual modality-specific encoders are encoded as Gaussians, so basically you're mimicking what we do in the standard VAE, but do that modality by modality. We can show that the overall distribution Q, so the product of these, remains Gaussian, and we know we have a closed form formula that tells us what the mean, what the overall mean and what the standard deviation is. Right, so we have this principal fusion here. And actually, that's quite interesting because if you now assume that all your covariance matrices are the same, or let's say even identity, just to simplify things, then your operation to get the mean, to get the mean of all the modalities taken together is just the average of the modality-specific extracted features, right? So we're going back to this HEMIS architecture that was proposed in MECA 2016, but now we have a probabilistic explanation for it by making an additional assumption that your covariances are the same for each of the modality specifics encodings. And now if you relax this kind of assumption that all the covariances are the same, then you get an extended fusion operation here. Okay, and now, in addition to dealing with multiple modalities, we can introduce really the missing modalities here by doing essentially some form of ancestral sampling. So we assume that we are given, we extend the model so that we have a mixture of Gaussians. So we draw independently the modalities that we have access to, and then we merge them together. And so this fits nicely into the elbow formulation as well. And great, so essentially we have this extended variational encoder-decoder strategy. One of the questions that was raised in the previous talk by Daniel, I think, is how do you deal with multiple scales? So we had this sort of similar questions in our case. So what we decided to do is not simply directly go for an encoding at a given scale. We decided to use sort of a unit structure, but cut it in the middle and have scale-specific encodings so that we would have this sort of multi-scale vision of the latent space as well. So there might be better ways of doing that, but this was a practical one that worked out well for us. And then, so once we have this kind of multi-scale extraction of the encodings, we can use this kind of product of Gaussians rule for the fusion of the latent spaces. And so basically, we have a number of encoders for each of the modalities. Potentially, we could have the segmentation as well, but in practice, we never have access to the segmentation as input, right? That's one of the outputs we want to get. So we encode all the available modalities with their modality-specific encoders. We average, or we merge, we fuse the latent space here, and then we can use decoders to kind of recreate the images. Right. And so here, at training time, here we normally have access to all the images and all the segmentations as well. So we can compare the output of our VAE with the full set of modalities and segmentation, even if at the input we're given only a subset of the modalities. And well, it turned out this works out rather well. So what you can see here are just exemplars, whereby, so for example, we try to reconstruct the flare on the first row, reconstruct the T1 on the second row, and get the reconstructed segmentation on the third row, given a different subset of modalities. So if you're only given the T1, then you can reconstruct something that looks roughly like a flare, but it's quite blurry, which is to be expected, because if you only have access to the T1, it's going to be a very sparse subset of information. But if you increase the amount of modalities you have access to, especially if you also give the flare as input, then obviously you reconstruct the flare much better as well. But you can see that across the reconstructions. So yes, we have access to reconstructions, but in essence, we don't really care about the reconstructed modalities. They're just byproducts, let's say, of our probabilistic model. What we're really interested in is to make sure that the segmentation behaves well, and because this will never be an input to our, in practice, to our encoder-decoder. And we can see that the segmentations behave rather well. And obviously, if you increase the number of modalities available for the segmentation, you get better results. But nonetheless, even if you miss some, you get decent results. Okay, so maybe I'll skip the technical evaluation, but trust me, it works okay and better than some of the other approaches. So yes.
So have you compared this one, like for example, the performance of the DICE score with respect to, for example, full data set versus some of the missing?
Yeah, so that's exactly what we did in the evaluation. So depending on what's available as input, we run so our algorithm. We compare it to the HEMIS as a baseline. So this is when we have access to all the modalities. This would be when we have access only to the T2 and so on. So we did all the combinations for testing purposes. And sorry. Which contrast is most important? I think the flare was the most important for. Yes. Okay, so that's kind of how do we deal with potentially missing modalities. The second topic that I mentioned was how do we do heterogeneous? How do we learn from heterogeneous data set? So again, here the goal is slightly different. In the previous part, we only wanted to do tumor segmentation. Here now what we want to do is use this kind of same set of imaging modalities, run this to a convolutional neural net, and get both tumor segmentation, but also kind of information about the tissue types. The challenge is that we don't have any ground truth for this sort of joint task. So, but we do have ground truth or training data sets for each of the individual tasks. So can we leverage that? This shows some of these individual tasks. So we start from the neuromorphometrics data sets that give access to brain anatomy for healthy patients. And we use the BRATS data sets for tumor segmentation obviously in patients here. So we'll call that lesion data set just for generalization. Another challenge here is a bit like the previous part. The available modalities that we have is different because per task they might again acquire different sets of imaging modalities. A third challenge is that actually if you look what neuromorphometrics calls a T1 and what BRATS calls a T1, they don't really look alike. Even if you're not an expert, you would see differences here. And actually, really a proper standardization of T1 does not exist in clinical practice. So these are the sort of things we need to deal with as well. Anyway, so how do we approach that problem? So for sake of clarity, we're dealing with two modalities here. It makes all the drawings easier and the notations as well. But so let's say we have a T1 and a flare. We want to feed that into a convolutional neural network and get at the output a segmentation of both tissues and brain structures. So the cartoon here represents this. If we would do that in a standard supervised learning framework, we would have a joint loss for all the tissue classes. But actually, most of the losses that we use for multi-class problems are actually one against all, right? So we can separate the joint loss into two losses, and that's very typical. Most of the losses would allow us to do that. So we have a tissue loss and we have a lesion loss, right? Nothing fancy here. We just pair the labels according to whether they correspond to the tissue or the lesion. Okay, so that's the first starting point. The second starting point is that actually what we're interested in these cases is really to work with patient groups, right? We're not interested in healthy controls. We're interested in patients. So we make the assumption that the data is stemming from the patient group. Now, if we look at our joint loss, which has been split into two terms, this is what we have. So we want to minimize the expected loss if we compare the output of the CNN with the tissue annotations, plus the expected loss of the output of the CNN with the lesion annotations. Okay, so the second part is actually easy in the sense that we just feed our images in the net. We have the ground truth annotations, and that's very standard supervised training. Now, the first part is a bit more complicated because actually we said we are missing the FLAIR modalities in the control groups. So how can we deal with this is the first question. So what we decided to do for this case here is to focus on a class of losses that gives us some nice properties, and this nice property we're after is actually the triangle inequality. Right, so not all losses abide by the triangular inequality, but some do, the Jacquard being one of them. And so if we have the triangular inequality, then actually what we have is that the distance between these two guys should be smaller than the distance between these two and the distance between these two. And here what we did is remove the FLAIR image, right? So we have another kind of bound on our loss. If we want to have this direct loss, we say that it's lower than this loss plus this loss, right? And so that's what we have in expectation here as well. And if you look at it in a bit more detail, so the first loss is actually what we call the heteromodal consistency. So lots of math, but what you can see here is this is the output of the network with all the modalities. This is the output of the network with only a single modality. And what you're saying is you want these two things to look alike, right? So irrespective of how many modalities you use, you want the same kind of output. And now the second term here is, okay, now we only have the T1, and we just want to make sure that the tissue segmentation works well. So it's standard kind of loss here. Okay. The problem, again, is that this expectation was on the patient case, on the patient distribution. And actually, we don't have the tissue loss on the patient group again. So we might have moved one step forward in the sense that now we've reduced the number of modalities we need, but we still haven't solved it. So we still want to use a control group, which is where we have the tissue annotations. So what we'll do is very simple, is we just assume that the T1s on the healthy part of the brain look alike on the two, on both the control group and the patient group, and we just make the assumption that on this part, the two distributions are sufficiently similar that we can assess, that we can evaluate that expectation on the control group, even if it's an expectation on the patient group. Okay, and if we're back to that scenario, the second scenario, whereby the T1s are different across data sets, and we need in addition some domain adaptation, but I will not cover this today. Okay, so that's what we do here. We just replace the expectation on the patient group by the expectation on the control group. And now we have all the ingredients that we need to actually train that complex model here. So graphically, this is how it looks. Right? So we have our neural network that can take several subset of imaging modalities as input. We have the lesion groups and the control groups. We sample a pair from each of these groups. We feed that to the network. Yes. Anyway, on top what we have is standard supervised loss on the control group using the tissue annotations. On the bottom part, we have a standard supervised loss on the lesion group for the lesions. And something to link the two things together is we have this heteromodal consistency loss. Right? So irrespective of whether we feed only the T1 or both the T1 and the flare, we want the same sort of segmentation as output. Great. And so validating this was an issue because I said we don't have ground truth for training. So how do we do that for validation as well? That's tricky. So we have access to one kind of unique data set where this is actually available. And we use that for validation. So that's the MR brains data. So it's not tumor, it's white matter hyperintensities. But nonetheless, here we have access to both the lesions and the tissue annotation. So, but a very small subset here, only 7 patients. Okay, so that's good enough for validation, probably not for training. Again, I'll spare the details, but essentially showing that things do work here as well. We then went on to try and apply that to the tumor cases. And we can do the same thing and learning from neuromorphometrics and BRATs together. But how do we validate that was another issue. So we created some form of data set that allowed us to validate some of the assumptions. So for example, in BRATs, so the tumor patients, many patients have a tumor only on one side of the brain. So what we did was find the symmetry plane, symmetrize the brain, and create pseudo-healthy looking brains there. And then we can run standard pipelines to do tissue annotations, right? So that allows us to get some form of information. We can also do tricks where we use, this GIF algorithm where we mask the tumor and try to feed that into a pipeline and so on. But in the end, we worked with one of our radiologist colleagues to annotate the results we had and see how consistent the results would be with what they would be expecting. And again, it's quite difficult to see here, but things are actually providing quite useful results, and we're starting to get one of the first algorithms where we can do joint tissue and tumor annotations here as well. Again, for the sake of time, I'll skip a bit the results, but if you're interested, you can look at the paper. So that's kind of how we dealt with heterogeneous data sets. The third topic that I wanted to address today was really how do we deal with user feedback, right? So we want these tools to be flexible not only in terms of what type of input they can deal with and what kind of training data set they can handle, but also how do they interact and how do they fit into the clinical workflow. And one of the first thing we did here was be able to provide annotations and user corrections at inference time to change the output of the segmentation. So the pipeline looks like this. So we start with images. We have an automated segmentation algorithm that gives us an initial segmentation. The user looks at the image. If he or she is happy, then that's it, it's done. But if not, then we decided to go for rather quick annotations in the form of scribbles. So essentially, if we see an over-segmentation, we pick the over-segmentation brush, just highlight a region where it's been over-segmented. We can do the same thing with under-segmentation. And now these simple scribbles are fed back to another algorithm that takes that into account to refine the segmentation. And this can potentially be looped until the user is happy with the output results. So that's kind of the workflow we work with. And so we were inspired by two classical ways of doing user interactions. So I'll show you two different ways of actually implementing that in practice. So the first kind of classical tool we used was that of geodesic distances, right? So because if you think of these scribbles, one kind of effective way of dealing with scribbles for segmentation is to compute the geodesic distance from every pixel in the image to the scribbles, and basically compare whether it's closer in terms of geodesic distance to a foreground scribble or to a background scribble. And so people have been using that for natural images. It works rather well. One of the problems there is that you start from scratch, right? So you can't combine that directly with an automated initialization, for example, and it works only on the contours here, so not much prior knowledge embedded in there. Nonetheless, we realize that this is probably a very good way of encoding user interactions in something which is more meaningful than just the scribbles themselves. So that's what we did in the first work. So kind of unrolling this pipeline I was mentioning in one step. So we have this automated segmentation first. We provide the scribbles. From these scribbles, we compute the geodesic distance of each pixel to the scribbles in the same way as we would do in the classical approach. And now we feed the geodesic distance maps together with the previous segmentation and the image to another convolutional neural network, right? And so this guy has to be trained beforehand, but nonetheless it can take inputs that are provided by the user. So therefore, at test time, we can use these to refine or to guide the segmentation outputs. So that's good, but what we realized when we first rolled out this is that sometimes the user would put scribbles in an area and the algorithm will not respect that. And this was super annoying for our users, right? They told us this was wrong, and after the next step, it was still wrong. So we had to fix that. And so to do that, we used, again, another kind of classical tool, which is a conditional random field. So conditional random field would provide segmentation based on some unary term and some pairwise terms here as well. So the unary terms that we use were basically the convolutional neural nets outputs, but to make them as hard constrained, we also put essentially infinite weights on the scribbles, right? So if the MRF doesn't agree with the scribbles, then then there's no way you can optimize this cost function here. So that's what we did. And then going back to some of the previous talks, so we have this regularization term in the form of these pairwise terms in the MRF, but finding a good way knowing exactly what the good regularization is complicated. So we designed kind of a free-form function to encode these pairwise terms and learn that learn the form of the regularization from the data we have, from the training data we have. So again, and then to get this free-form function, we plug a mini neural net, so not convolutional, but just we're training a free function essentially to encode this regularization term here. Okay. Oops. Great. So this was one thing, but then we realized that still this was not sufficiently flexible in the sense that if the image protocol was slightly changing, our pre-trained algorithm was not coping very well here. So we took a step back and looked at other ways of doing interactive segmentation, and again looked at GrabCut, which is one of the very successful kind of scribble-based approaches for doing segmentation. And what GrabCut does is essentially it learns a model of the image on the fly. So it creates a GMM model, so Gaussian mixture model, to encode whether the colors within the image are representative of foreground or background, and then uses a conditional random field to regularize, spatially regularize the segmentation output. And it works okay, but still you have to give it a lot of interactions to actually get to a result. And it's fine if the images are very prominent, but in medical imaging it's not usually the case. So one of the questions is, can we use the same kind of formalism, but take advantage of the representation efficiency of neural networks? So if we want to do that, we want to have something that works, but nonetheless it's not too flexible, because we were going to learn on one single image. So what we did was pre-train a segmentation network, and then arbitrarily decide that the first part will be a feature extractor and the second part will be a classifier, so that we reduce the number of parameters we are allowed to retrain on the fly for a given image. So essentially this part now is what replaces the GMM in GrabCut. Okay, so the pipeline looks like this. So we have a bunch of training images where we have bounding boxes and segmentations, and we learn our convolutional neural net from this. Now at testing stage, so we feed the image and a bounding box. So we get an initial results, we provide the scribbles, and then from these scribbles we retrain our neural network based on the scribbles, right? And this gives us an output. And again, we use the same kind of tricks of having a conditional random field to make sure that the hard constraints are met. And we also use some of the geodesic distance maps, so that when we retrain, we know which region to trust or not to trust. So in a way, we're doing overfitting on a given image, but it's willful overfitting. We know what image we want to segment. We have scribbles on there, so let's overfit on it. Yeah, I'll skip the derivation, but essentially it's really the same thing as GrabCut, where we start with an overall energy minimization, and then we alternate between optimizing the weights. Sorry, we optimize between for a given CNN output, optimizing the segmentation that meets the CRF, and then once the CRF is fixed, retraining the weights of the neural net, and we iterate this. And so, yeah, so it works quite well. So this is an example, again, on brain tumors. So we load the images, so 3D images here. We get an initial segmentation. It has to be rather quick because it's interactive. So here we see that some of the errors were made. So we provide these scribbles. In 2D, we can run the retraining on the fly. In 3D, we wait. It takes a bit more time, so we wait for the user to provide all the scribbles, and then push update, so that we retrain the network on the fly here. And yeah, and that's it. And so if the user is happy with the segmentation, we can continue and do something else. So just to show some of the results here. So we show that by introducing these scribbles, we get much better than just having a CRF to regularize the output. But also one thing that was interesting is we can also do some unsupervised retraining, image-specific retraining here. So yeah, so that's it for the talk. So in conclusion, so these were kind of snapshots of some of the flexible machine learning tools we've been designing in the lab. So I put aside some of the more kind of really intraoperative things that are a bit less principled, and I thought would be of less interest here for this audience. But we can use that as well on intraoperative, or these sort of concepts in intraoperative imaging, and linking that to, say, robotics as well. But to really make this happen, we need multidisciplinary tools where we understand what the clinicians really want, what their, how do these tools are embedded, how would these tools be embedded in the workflow, and how do we merge this kind of information in a way that's actually usable in practice. So, thanks.